We all know AI is getting incredibly good at writing code. But with all that code, there's a huge question. Where does it come from? And what if some of it is copyrighted or has usage restrictions?
That's a major concern. Large language models for code, or LLM for code, are often trained on massive datasets scraped from the internet, including open-source repositories and even private code. This raises big questions about intellectual property and unauthorized use.
So, how do we even begin to check if an AI model has been trained on restricted code? Is there a way to audit its memory?
Exactly. That's where membership inference, or MI techniques, come in. Think of it like trying to figure out if a specific ingredient was used in a secret recipe just by tasting the finished dish. MI tries to detect if a particular code snippet was part of the model's training data.
Okay, so MI is the detective. But what if someone tries to trick the detective? What if they change the code just enough to hide its origins, without actually changing what the code does?
That's the core of our research. We investigated semantically equivalent code transformations, or SECs. These are changes that alter the code's syntax, like renaming a variable or reordering statements, but don't change its underlying functionality or meaning. It's like swapping sugar for honey in a recipe. The dish is still sweet, but the ingredient looks different.
So, the question is, can these transformations make it harder for MI techniques to spot the stolen code?
Precisely. We ran experiments applying 23 different sect rules to Java code, and then fine-tuned several LLM for code models. The first crucial finding was that these transformations barely affected the model's accuracy. The drop was minimal, usually less than 1.5% in the worst case. This means transformed code can effectively replace original code for training.
That's a big deal. If the model still performs well, there's no penalty for using the altered code. So, what about the MI detection? Did the transformations work?
Our results were quite striking. We found that one rule in particular, rename variable, was exceptionally effective at reducing MI success. In one case, it reduced MI detection by over 10% on a DeepSeek coder model, while only causing a 0.6% accuracy drop. You can see an example of how this works in Figure 1 of our paper, where MI successfully identifies the original code, but fails after renaming.
Wow, so just changing variable names can hide the code? That sounds like a significant loophole. What about combining multiple transformations? Does that make it even harder to detect?
That's an interesting point, and our causal analysis, which you can see modeled in Figure 3, confirmed that rename variable had the strongest single effect. Surprisingly, applying multiple transformations together didn't significantly increase MI evasion beyond what rename variable achieved alone for most models. It suggests diminishing returns.
So, a simple change can be super effective, but a bunch of complex changes might not add much more protection against detection. What does this all mean for the future of AI and code?
It exposes a critical vulnerability. Current MI techniques, which are our main tools for enforcing license compliance in LLM training, can be substantially weakened by these semantic-preserving obfuscation methods. This means we need to develop more robust MI techniques that are resilient to such transformations, or find new ways to audit model training data.
So, the cat and mouse game continues, but now we know the mouse has a very simple, yet effective, trick up its sleeve. This really highlights the need for ongoing research into AI security and ethical development.